We are Group 3. Myself, Anisha Menon. Register number NSS17CS017. Our project is Real-Time Traffic Detection from Tweets. We are guided by Assistant Professor Chitra. Yes, ma'am. In this grateful occasion, I would like to thank her. Thank you so much, ma'am. So let's move to our presentation. So, we all know that we are living in a fast society. Everyone need to do or go or buy whatever in a quick manner. We got easily distracted or even fall into a mental breakdown when we became late. So, for this fast society, we are planning to build a new system that means a real-time traffic detection system, which uses the social media, on here it is Twitter, as a social sensor to detect the traffic in a more effective and in a dynamic way. So, the obvious question that comes to everyone's mind is that why Twitter? Twitter is considered as a global social media giant with an overall of 340 million users with 186 million active daily users across the globe. Twitter break the record of 500 million tweets which was posted per day. According to the research which was conducted by American Press Institute, it is found that 64% of the Twitter users claims that they use the Twitter to get and share news. So rather than a social media, Twitter became a fastest news source for millions and millions of people in nowadays. And also the credibility ranking for Twitter is considered as 4, which crosses the 3 major social media giants like Facebook, Instagram, and webmail. So for our project, Twitter is one of the best and perfect choice. So, what is our project is that? A system which collects the tweet from user and then apply various pre-processing steps and then feed it into a pre-trained CNN model and predict whether the tweet is traffic related or not. It also showcases the location of the tweet. Along with this, it is done with the help of Twitter APIs as well as some geocoding techniques. The existing models are basically hardware models and machine learning models, and our system outperforms those with an overall accuracy and F1 score as 98%. So that's all about. Handing the session to Helan for more. Thank you.
Thank you, Anisha. Myself, Helan George, NSS 17CS029. I'm going to talk about existing methodologies and the need for proposed methodology. Existing methodologies available for traffic detection are either hardware-based or machine learning-based models. And here I'm going to talk about one such existing methodology, which is a machine learning-based model. In this model, first input the raw tweets from Twitter. For that, fetch the tweets from Twitter using a REST API, and then these raw tweets are fed into the next stage, which is pre-processing. In pre-processing, first step is segmentation, which is converting the tweets into tokens, and then the stop words are filtered. Next stage is word embedding. This model uses one-hot vector representation of words. Next step is padding. After that, classification. This model uses SVM classifier for classification and then get the output, that is whether there is a traffic or not. Next is need for proposed methodology. When the existing methodologies are taken into account, many shortcomings are known. Primary disadvantage is the use of bag of words illustration of text. It suffers from shortcomings such as vocabulary. Vocabulary needs a careful design to manage the scale, which affects the sparseness of a document representation. Sparse representations are tougher to model, each for computational reasons and for data reasons. Discarding word order ignores the context and meaning of words within the document. There are some limitations to the machine learning model as well in case of finding hidden patterns in data. Next, I'm handing over the section to Kadeeja. Thank you.
Thank you, Helen. And hello, I'm Kadeeja BH, NSS17CH032. Now let's move on to the system architecture. First and foremost, as the diagram depicts, we will be extracting tweets from Twitter using Twitter API requests, and then the collected tweets will undergo pre-processing where it removes emojis, punctuations, and stop words. Next, we will head on to the representation where word embedding and padding takes place. Afterwards, onto the classification where it is passed onto the 5-layered CNN model, and finally the traffic-related tweets are captured. Next slide. Now let's look on to each method step by step. First is the data acquisition, where we collect data. We have procured it from Mendeley data by Dabry, S. and Heaslip. And there is a Twitter API request where TweePy is used for accessing Twitter API. Then there are also the methods and attributes used. Secondly, pre-processing where tokenization is performed using word tokenizer. Here we remove emoji, URL, and other special characters. Also, we perform stop word filtering. Next, we move on to representation part where word embedding is performed using word to vec and later padding. Next slide. Then we come to classification where we employ a phi-layered CNN network as our model with consecutive layers like the embedding layer, secondly convolution layer, then third pool layer, dropout layer, and dense layer. Finally is a web representation where we make use of Django for web representation for our project. Now I'll hand over to Helen for the rest. Thank you.
Thank you, Kadeeja. Myself, Helen. Now I am going to take you through our code. First, we import all the libraries required. First step is pre-processing. We need to clean the raw tweets. For that, we defined 4 functions to remove all the emojis, punctuations, URLs included in the tweet. And then we read the dataset using readCSV function from pandas and convert them into data frame. And then removed all the emojis, punctuations, URLs by using the function defined above. Next is tokenization. For that, here we used a word tokenize function and the output is shown. After that, all tokens are converted into lowercase as shown. Next is stop word removal. We remove all the stop words using the function defined. Next, we split our training dataset into two, one for training and the other for validation. Split ratio is a 20% for validation and 80% for training. Next cell. Here we find the maximum training dataset length and the total number of words for training data and printed below. The maximum length for training data is 24. In the next cell, we find the maximum sentence length and total number of words for validation data and it is 21. Next is padding. Here we used post padding. Next we load all the vectors from Word2Vec Google News 300 using API and then find all the vectors related to traffic and they are printed. Next we find an embedding vector for all the words in training and validation set with a embedding dimension 300 and then build an embedding layer using embedding function with a maximum length as a maximum training sentence length. Next I'm handing over to Kadeeja. Thank you.
Thanks again, Helen. Now, to construct the model, we add on layers. There are 5 layers as discussed before. So let's talk about the very first layer, that is the embedding layer. Here it takes the input length equal to sequence length. It takes input of length 20 and for each input index it creates a 100-bit embedding, and before that we instantiated pf.keras sequential model over here, and the max number of features or indices are actually 20,000 plus 1, and for each input index present it creates a 100-bit embedding. So next we have convolution layer. Here we add on 1D, one-dimensional convolution layer, and it has 128 different convolution filters, and the activation is ReLU, which is rectified linear unit activation function. It's a linear function that will output the input directly if it is positive, otherwise 0. So it has become a default activation function because a model that uses it is easier to train and often achieves better performance. So as kernel size is 3, sequence length 20, it would look at 3 words at a time, the next 3 words, and so on. Here we have a global max pool layer to get the most important features. Then we have used dropout layer to reduce the overfitting. It is necessary because large neutral nets on relative the training data, which can result in poor performance when the model is evaluated on new data. Then we have a dense fully connected layer for the final classification. Here we have a one neuron for output for the two classes. So the activation is sigmoid here. And the main reason why we use sigmoid is because it exists between 0 and 1, especially useful for models where we have to predict the probability as an output. We have added regularizers for the embedding weights, for the kernel weights, for the bias weights. This prevents overfitting by the regularization process. We have used L2 regularization for the same. And at last, we used model.summary, which prints the summary. So let's take a look at the summary. Yeah. So the classes are categorical, and as seen before, we have used categorical cross entropy as a loss for CNN. And if we take a deep look into it, we'll find that embedding layer, our sequence is 24 for each value. We have 300 bits as our output. That is a 300 dimension vectors as our output. And this is given as input to the convolution layer, which is one dimensional layer. So the output convolution layer is 128 filters and 23 dimension as our output. Then we have the dropout layer of the same size. Yeah, then we can see the parameters, the trainable parameters and non-trainable parameters as well. And in the very next cell, we see that we perform training. Firstly, we convert the entire thing to an array. We perform fitting, running epochs, and also find accuracy. And for that, we have xtrain, which performs data training, and xvalid, which performs data validation. Likewise, we have L labels for label training and L validation for label validation. All along, we have batch size of 64 and runs 20 epochs, and to find the accuracy and loss of validation set. Yeah, that's it. And now I'll hand it over to Anu. Thank you.
Thank you, Kadeeja. Myself, Anu Anto, register number NSS17CS019. After training our model, we have plotted the loss and accuracy graph. First, we have plotted loss graph for the training data as well as for the validation data. If we look at the graph, we can see that the loss is decreasing. Next is the accuracy graph. If we look at the accuracy graph over here, we can see that the accuracy is increasing from 0.9718 to 0.9805. Then by using model.save, we have saved our model in model.h5. After that, by using our model, we made probability prediction on validation data and keep only the probability prediction for the positive class labels. Next is ROC curve. It is a plot that evaluates a set of probability predictions made by a model on validation dataset. The false positive rate is plotted on the x-axis and the true positive rate is plotted on the y-axis. A diagonal line on the plot from the bottom left to top right indicates the curve for no skill classifier, and a point in the top left of the plot indicates a model with a perfect skill. The curve is useful to understand the trade-off in the true positive rate and false positive rate for different thresholds. The area under the ROC curve, also called AUC, provides a single number of to summarize the performance of a model in terms of its ROC curve with a value between 0.5 indicating no skill and 1 indicating perfect skill. Here we have used a geometric mean as a metric to locate the threshold with the optimal balance between false positive rate and true positive rate. The best threshold value and G-mean value obtained is shown over here. Next is plotting the confusion matrix. The true negatives we obtained is 5012. The true negative, false negative, and true positive shown over here. Next, we have reloaded our saved model to a new model. Next, we have after that we have printed a table of precision, recall, and F1 score for positive and negative labels. Next is PDF. Here is the summary of the results we have obtained. First graph is accuracy graph. Next is loss graph. After that, we have printed the ROC curve, then the precision recall and F1 score table. Thank you. Next part will be taken by Anisha.
So, thank you so much, Anu. Myself, Anisha Menon. So, the framework that we were used on here is Django. The reason why we use it is our project is highly expandable. That's why we use the Django on here. So, these are all some of the modules that we were used for our projects. And as like Anu already said, the model is got saved as model.hy. And then we loaded that model into our reconstructed model. So the next part is to create an index page. So our index page is home.html and it will be look like this. So there is a button called as detect traffic. So by clicking on that button, the model will redirect it into the output function. So what we done on this output function is that it basically fetch the data for real-time prediction. So it is done with the help of a TweetPy. So there are some private keys which was obtained from Twitter, and with the help of those private key, we authenticate the user. And there is a query list. Query list basically contains a list of keywords that are directly related to road traffic. So since I already said that we are mainly dealing with traffic, location is one of an important parameter. So to fetch these location related details, we use the GeoSearch API. So the important step, that means the fetching of a Twitter. Tweet fetching is done with the help of a tweetpy.cursor. So with the help of a tweetpy.cursor, we fetch the Twitter that is related to the keywords that is given on this list in the New York City. And in that way, we collected 10 tweets from each of these keywords and store it in a JSON format. So the next part is filtering the tweet. So for that, we created a CSV file called as tweet.csv, and we apply some timing constraints since the traffic data is highly related to time. And the New York, according to the New York researchers, the New York road traffic is for around 55 minutes. That's why we apply a small filtering regarding time on here. And after that, we write the details like created. That means the time of tweet is created, Twitter ID, location, as well as the tweet to that CSV. So after writing it into the CSV file, the next process is pre-processing. Pre-processing is already talked by Helan. It basically include the removal of emojis, URLs, punctuations, tokenization, stop word filtering, and padding. So after the padding is over, the model is get reloaded, and the probability of the model is get. So the probability is get predict proba, and the probability is obtained, and then after the prediction is over, the predicted result is also get saved into tweetfinal.csv, and after that we render the tweetfinal.csv file to our table.html. So our final output will be look like this. So it contains the tweet, their location, as well as the prediction. That means whether the tweet is a traffic related or not. Handing the session to Anu for more. Thank you.
Thank you, Anisha. Myself, Anu Anto. Next, I will be talking about our conclusion and future work. Based on the results of design, analysis, and evaluation of the experiments, it can be concluded that the model has successfully tested with an F1 value of 0.98. Using word embedding in the proposed model as an effect on the F1 score value, it has increased from 0.95 to 0.98. As a future work, we can collect more data for classifying traffic-related tweets into detailed categories like traffic accidents, traffic status, etc. And we can also use deep convolutional neural network for short message classification. Next slide is timeline. The details, we have completed our project in this timeline shown over here. Next is references. These are our references. Thank you. Thank you all.